Alright, it would be a good review to do the indefinite integral of this. So pull the 6 out front, cosine of 3t. And then we need to do what to get the integral of that?
Do 1/3 sine.
Yeah,
Is
so
that what you're talking about?
yep.
Okay.
Call u 3t and then dt equals du over 3. And go up there. So we get 6/3 integral of cosine of u du. Which is what? What is the integral of cosine? Sine. Yep. Alright, so 2 sine t. And I guess we're not doing the definite yet, so plus c. Okay, and then we plug in 0 and we hope to get 5. So, yeah, because this whole thing is 0. I'll save myself some writing. Okay, so that is S of t. Okay. And then what is the value of S of pi over 2? We just plug that in. So 3 pi, so sine of 3 pi over 2 is -1. So this becomes S of pi over 2 times 3. And that is measured in yards. Yards. What a weird unit, huh? Yards. Yards per day. I wonder what this could be. Like a glacier, maybe?
Yards per day. Yeah,
That's probably too fast for a glacier.
Yeah, because my glacier's like a couple of inches.
Yards per year, maybe?
Yeah.
Something slow, though, because pi over 2 days is...
It's a sin.
That's over a day. We've only moved 3 yards. A sloth. Yeah. Anyway. All right, so net change, that's another way of wording displacement. And so which version of do we use absolute value, do we not? Like which version of the total integral do we do for displacement?
Don't we just do the regular integral
Yep.
without any absolute values?
Yeah. So didn't we already do that?
Kind of. Because we found the solution to the indefinite integral. But we want how far it's traveled over between 0 and pi over 2.
Of v of t.
Of v of t.
By the way, when I was grading some more of the mock yesterday and paid a little bit closer attention to the fact that it does say, like, having the correct integrand is one of the points on a lot of these. And they specify specifically that you can say this is the integrand. For these definite integrals, you don't have to write out the function. You can do that, it's either one, but they actually did say that specifically. I think this is what you just said, right?
Yes.
Okay. So, what'd you guys get, just so we can save some time here?
I got -2.
Just solid -2?
Yeah.
Okay. And that would be also yards. Okay. Total distance traveled, let me circle all 3 words. So now we're doing same thing.
The absolute value.
Yeah. So this will account for the negatives and the positives and all that. What'd you get on this one?
6
Okay.
yards.
Cool. All right, so kind of just putting that together. Go back a couple of pages to finish that last example because number 4 has a graph, but sometimes it won't. So I think just going to skip this one and say C number 10, and we'll just call that our example where we did it by hand.
Okay.
If that's okay. We can do it. You guys want to do this one, or are you okay to not?
And
Okay, let's just do it. That's true. Good point. All right. So I said yesterday we should do this by hand. And now x of 1 is negative 2. So we have, remember, an accumulation function. It accumulates up to the point we're given, and then we have to figure out the rest after that. So we'll have negative 2, and then plus the integral of 1 to 2 of v of t. But this time, since we're doing it by hand, let's go ahead and write it out. So t to the 4th minus 2t cubed plus t and plus c. Let's see, I should label that x. So x of t. Okay, so how do we find c in this one? Or do we have to? I wrote a c, I shouldn't have. Because we had a definite integral. So
Yeah.
never mind. This is going to be a lot of space. So negative 2 plus okay, so lots of little stuff. Sure is right. Why are we putting the negative 2 out front again?
because that's our initial condition.
I guess you could kind of say that. That's the accumulated total up to 1.
Yeah.
And then we're accumulating the rest of it from 1 to 2.
Right.
So it's not the initial like at t equals 0 condition, right?
Okay. So it's just
Yeah.
total accumulation up to that point.
Up to where we start integrating. Alright, so we get 16 and then minus 16, so that's 0. So 2, and then 1 minus 2 is negative 1 plus 1, that's also 0. Well, that works out nice. Hey, hold on a second. Okay, so this whole thing is a nice big old 0. So this one is kind of interesting. So I want you to pretend we don't have the graph for a second. So what is the total distance traveled by a particle during the first 4 seconds if the particle's velocity function is this? And we know, well, first this is a linear function with a downhill slope. We know that because we saw the graph, but know that anyway, right?
Right.
Which means that it could potentially cross the x-axis, and then we're integrating space down here, which how do we have to count that? As negative. So if we go back to the problem from yesterday with the guy driving around, sometimes he was going the wrong way, but how do we know where that occurs?
set p of t equal to 0.
Yeah, so we have to find those places where, and maybe it does it a couple times, find those places where the function changes from positive to negative, so that we know if we're subtracting or adding, okay? And then total distance, though, we need to do what to get that for the negative parts?
Absolute value of the integral of d of t.
Yeah, of the whole thing.
Or absolute value of d of t, to take the integral of it.
Other way around, actually, you said it right the first time. So it'll be this.
Absolute value of the whole.
Yep.
Oh,
And the reason why is because if we just do the inside part for each piece, like if we just did the absolute value on b of t, what am I trying to say? We want to take the positive distance, even though we'll get a negative value for the negative piece, is what I'm trying to say. So find the distance, it will be negative, then make it positive to get the total. And since we're doing this in pieces, because we're going to integrate like here to the 0,
Okay, I
like
see what you're saying.
that section, and then that section will be separate.
So you're saying find our where x equals or y equals 0. Find our x-intercept and then plug in the integral up to that point. That's positive, and then plug in the absolute value of the integral after that point.
Yeah.
Okay. What would be the difference between just taking the integral of the absolute value of the inside?
I don't think there would be one, actually.
Okay.
But we can do this by hand if we stick it on the outside.
Oh, I guess that makes sense.
Well, because,
we don't know how to take it.
like, do you know how to do the integral of that? The absolute value of something? Because think about it, we would have to do like the absolute value of u and make this be u, but we haven't learned the
Yeah, I guess that makes sense.
the integral of an absolute value.
So if you're doing it by hand, you have to isolate your.
Yeah. If we did it on a calculator, it wouldn't matter. We could do this, but
Okay.
by hand we have to put it on the outside so that we can do it. Because then you can just do that at the end.
Gotcha.
Yeah. So, I'm going to write the note out here because we won't have the graph. Alright, so we're integrating that piece and then adding it to that piece, but absolute value of that whole thing. Now, you could put the absolute value on both, or if you had more than one, you could put the absolute value on all pieces, so you don't have to worry about which one is positive or negative. I'm going to write that over here as a note. So put the absolute value on all the pieces. Because like I said, we have a graph right now, but we won't always know which one's positive. There's a lot of little marks on this thing now. Probably be easier to make the 1.5 3 halves.
Yeah.
So negative 3/4. Oh well. So this will just be 2 minus 0. Like plug in 2 and then the whole thing, the second half is 0 is what I meant.
Yeah.
So t squared is 4 over 2 is 2. So negative 3 plus 6 is 4.
It's 3. Negative 3 plus 6 is 3.
Okay. And then, what do we have over here? 4 squared over 2 is 8. Times negative 1.5 is negative 12 plus 12. So that's 0. And then plug in 2. So shouldn't this be 3 too? 3 also?
No, I got negative 7 for that, because I got, for the first one, when I plugged in 4 to the 1.5, I got negative 6. Because if you take t squared, that's 16.
Over 2
Over 2 is 8, and 8 times 1.5.
is negative 12.
Oh, I think I did 6. No. 4 times 1.5.
Okay.
It is. You're right.
And then plus 12, so that's 0. And then the 2 should be the same value. We did a lot there without writing it, so are you good on where that all came from? Okay, so the big idea of that one is be able to do it without a graph. And if you find the zeros and then put absolute values on everything, then you're safe. Because it doesn't hurt the positive ones, but then you'll for sure catch the negative. In case we had a more loopy function that has multiple positives and negatives, or maybe 2, if it was like a parabola,
Yeah.
and it has 2 positive sections and a negative, you don't have to try to figure out which ones it is necessarily. Everybody good with that? Okay. All right. Are you good if we move to 8.3, or do you want to? Are we going too much? Are we good on that? 8.3 is kind of a continuation of this, which is kind of nice. So kind of a nice little saying up here if you want to use it. So if we integrate, let's say, a velocity. So we've done this, right, now?
Right.
What does it mean by a net change?
Means your position, so it essentially is saying how far you moved from this point, like during this time period.
And how far is it from where you started, right?
Yeah.
So it's the displacement concept. But everything that we're not always going to do it with lengths and velocity. So like this first one, we'll get to it in a second, but you can see it's sand being washed away instead of distance and displacement. But integrate a rate of change, you get a net change. And we could just say it's like a displacement I feel like every time I write on these things, I'm bumping up against some kind of space issue. So I'm saying like a displacement because it's not specifically that, right? So this one's kind of interesting to me. So a storm is washing away some sand, causing the edge of the water to get closer to a road. So the rate at which the distance between the road and edge of the water, was decreasing during the storm is modeled by this function. So it's a rate in feet per hour. And so the edge of the water was 200 feet when the storm began. So we can read that as an initial condition, but we can also read it as like a something to zero, like, right?
Right.
Like the accumulation before we start.
You can also use it as a point if you need to take it up.
Yeah. So if the storm lasted 4 hours, how far is the water from the road after the storm? So, thoughts on how to do it?
So that's a rate. You would say 200 plus the integral from 0 to 4 of e to the negative side of dt.
So I'm going to do distance. Okay, now you have the right idea for sure. I'm just going to change one thing. Remember two things really. Remember we can write R of t.
Oh, yeah.
2, you said minus here, or plus here, but it should be minus. Why?
Oh, I guess because it's being eroded and your 200 is subtracted from the 200.
Yeah. That's a little bit subtle. I think it's hard to catch sometimes
Yeah.
because it seems like we think of the water getting closer to the road as positive or plus.
Yeah.
It should be minus because this is think of if here's our road, the water was over here, 200 feet away, but now it's getting closer. So it should be taking distance away. Yeah. Which, it's like all dependent on the perspective. Like, are we thinking water getting closer? To me, that's plus. Or road, the water's getting closer, that's minus. So, yeah, just have to read carefully. Even then, sometimes it's confusing. And so we can do this on a calculator. Just don't forget your 200. Okay, so 196.937. How would we write out our answer to this?
So we would say
Well, that's a good question. Like, is that how much we moved closer, or is that the total distance now?
that's the total distance from the road up.
Okay.
So we would say the water after or
Sure.
at T equals 4.
I like after 4 hours. Okay, the water.
Is 196.937.
Nice.
Doesn't seem like a lot, but 3.5 feet is it's a lot of ground.
Yeah. Yeah, I'm trying to picture how that would, how it would work to erode sand and get water closer. I guess if it's forming like a embankment kind of or something.
I would see almost like a flash flooding kind of thing, where it just runs back into the body of water or the river, but it erodes the sand away.
Yeah, that's true. Good thought. Cool. All right. So stores having a 5-hour sale. The rate at which shoppers enter the store T hours after the sale is modeled by the function E of T, which is measured as shoppers per hour. When the sale starts, there are already 70 shoppers. We don't have to solve this one. So write an equation involving an integral to find the time x when the number of shoppers in the store is 200. And then assume nobody leaves. You guys want to try that one since there's no calculator?
Yeah.
Alright, so what did you guys put?
200 equals.
You said 70 plus? Huh?
I said integral from 0 to x equals, or E of T.
I put 0 to 5.
Good. And do be careful, like you were pointing out, that your integral is with respect to t, even though we have x's floating around.
Why is it?
Huh?
Oh,
You're good?
yeah.
Okay. Alright, next one. This will be a little bit of review. So, we're pumping water into a tank. Haven't you missed the water pump and tank kind of problem? Oil, yeah, it's leaking or pumping in. It's like so many of those. So R is differentiable and decreasing. So anyway, at time 0, there's 5,000 liters of water in the tank. So why do we look at the table and see 0 time and 3,000?
Because R of T is a rate.
Yeah. And I feel like these are ways that AP can take a the calculus and mess you up because you're in a hurry and you don't see that, right? Or you read over it.
Wait, so then why did they tell us about 5,000 liters? Is that just irrelevant information? Or is that
It's not, no, because that would be considered, well, liters is what kind of measurement? That's a volume, right?
Yeah.
So, what happens if we integrate liters per hour?
You just get liters.
We get volume. So that's 1 up, right? 1 layer up. So this functions potentially as a initial condition.
Right.
Yeah. And I say potentially, not because it's wrong, just because like that's what you need to think when you read, like, oh, this could possibly be an initial condition for a volume function. Okay, so this is kind of interesting. We're taking the integral of r to get what? So what does it represent? And this is a definite integral.
Right, so it's representing the amount of water gained between 0 and 8.
Okay.
Excluding your initial condition of 5,000 liters.
Okay, so let's be a little more specific. I'll write this part. The total volume of water. What? Is it, can we say total volume of water in the tank?
No,
Okay.
the total volume of water added to the tank.
Yeah, good. So pumped into the tank. In the first 8 hours. So make sure I always talk about the time. All right, remember Riemann sums? How do we do a left Riemann sum?
Take your left, take 3,000, or I guess it would be 2,500 minus 3,000 times 0. So you would start with your, or wait, no,
Not
I'm
times
doing it backwards. It would
Yeah.
be 1 minus 0 times 3,000.
Good. So I'm going to just write kind of the reminder is width times height of what? Of the left boundary.
Yeah.
And I put the sum symbol. Good. Okay, so like you said, it's 1 minus 0. Let me write that better. 1 minus 0 times 3,000 plus, what's the next one? 3 minus 1 times,
2,000.
yep, times 225.
It would just be times.
Because it's the, we're making, remember we're making left rectangles? Yeah, good. Okay, and then 6 minus 3 times 2,100. And 8 minus 6 times 1,500. So we get 3,000 plus 5,000, so that's 8,000 plus 6,300 is 14,300 plus 3, so 17,300. And what are the units of 17,300? Yeah. Everybody good on that one? Okay. Now it's asking for the total volume in the tank. So,
We just
Just
add our
add 5,000.
conditions.
good. Do you do this with math with your tanks that you have at your house?
No.
Make a little table.
Take an integral of your total volume. It'd be kind of fun to do, huh? I guess we're out of time,
I
so
don't know, fun is the word.
yeah. You'd rather just be filling it up and getting it over with?
Yeah.
Yeah. How long does it take to fill one up?